Okay, good morning everyone. So yesterday I have explained to you the basic concept of limit. So today I'm gonna explain to you something that is more deep than yesterday. Actually it's the same, but it's more mathematical. There are more terminologies used during this lesson. So basically it's a graphical and algebraic approach to the definition of limit. So, and it's on your book page 34, and this is actually the continuity of what we have learned yesterday about the basic concept of limit. Okay, so now open your book page 34, and before page 33 I have taught you the verbal definition of limit, which is L is the limit of fx as x approaches c if and only if you can keep fx arbitrarily close to L by keeping x close enough to c but not equal to c. Yeah, so on this chapter, on this lesson, I'm gonna teach you the mathematical definition of a limit, which includes the letter epsilon and delta. Yeah, don't get confused. I'm gonna try to explain to you now. Now look at so I want to review first about yesterday's lesson. So this is x, if this is y, and let's say I have a graph like yesterday. Let's say it's like this, and it's 2,3. If I'm it's 2,3, and this is fx. Okay, so the limit of fx as x approaches 2 is equal to 3, even though f of 3 is undefined. So again, limit is not the exact value of the function, but limit is the value that is approached by fx as x approaches certain number. In this case, the fx is approaching 3. The fx is approaching 3 as the x is approaching 2. The graph is approaching 3 as the x approaching 2. Okay. Now, epsilon and delta. So the definition of limit, I'm gonna read it to you first. The definition of limit on your book page 34. L is equal to limit of fx as x approaches c if and only if for any number of epsilon is greater than 0, no matter how small. There is a number of delta which is greater than 0 also, such that if x is within delta units of c but not equal to c, then fx is within epsilon units of L. Okay, now let's start with delta first. So actually, what is delta? What is epsilon? Let's start with epsilon first. What is epsilon? Epsilon is the distance between the limit value and a certain y value. So we have here the L is equal to 3, right? I'm going to draw a horizontal line. L equals 3. Okay. So delta is defined as the distance between this y equals 3 to a certain value of y. So if I define the epsilon is equal to 0.5, for example 0.5, then actually it's gonna be here and here, which is 3.5 and 2.5. Okay, 3.5 and 2.5. So this is epsilon and this is epsilon. Let's name it epsilon 2. Well, epsilon is just epsilon. There is no epsilon 2 and epsilon 1. I'm sorry. Okay. Now, as the epsilon is 0.5 in this case, now of course the value of this 3.5 and 2.5 will correspond to the certain value of x, right? So let's say that it intersects the fx here. So if I bring it down, then maybe, just maybe, the value of this is maybe 2.5. Okay, 2.5. And the same thing with the 2.5. It's 2.5 here, it beats the graph here. And if I want to try to find the value of x, then it might be, maybe let's say it's 1.5. Okay. So what is delta? In this case, the delta is the distance between the C, which is the x equals 2, the C is 2, with this slide. So this is delta 1 and this is delta 2. Okay. So in this case, the delta 1 is equal to 0.5 and the delta 2 also is equal to 0.5. Okay. Now let's try to get back to the definition again. I will try to explain to you again. Now, limit L is equal to limit of x approaches C of fx if and only if for any number of epsilon greater than 0, no matter how small, then there is a number of a delta greater than 0 such that if x is within delta units of C but not equal to C, then fx is within epsilon units of L. So basically, what it's trying to say is when you make the delta smaller, when you try to make the delta smaller, then the epsilon must be smaller also. Okay. As it's very close to the value of the C itself, then the value of the limit, the L, must be also at one point. Okay. So if that happens, if this red arrows, if delta is approaching C and L is approached at one same point, then we can say that the limit does exist, which is equals to the L itself. Okay. Now I'm gonna give you example where the limit doesn't exist. Let's say that I have another graph. I have it like this. Oh, make it easier. Okay. Now, if this is C, if this is C, the one that we want to find the limit, let's say this is C, and I have a delta, let's say this is my delta. So this is C minus delta, and this is C plus delta. Okay. So I will have it. I will have it here, which is, and I will have it here. Okay. So I will write it as f of C plus delta. And this I will write as f of C minus delta. Right? Okay. Now, look. When the delta is getting smaller, into C, what happened to the first, the f of C minus delta? The f of C minus delta will go to this direction, right? Because when it's going here, then it goes this way, right? So it's going to this way. Now, what happened to the other side. To the other side, when it's approaching this way, actually the epsilon is also approaching going up here. But when the delta is very close to zero, when the delta is very close to zero, then actually the epsilon is, then actually the limit, the epsilon is not getting to the same point, right? The one is getting here. This is the one. And the second one is getting here. Now, if this case happens, then actually, like I said, because there is the delta is there, but we cannot keep the function within epsilon units because it's totally different. One is here and one is there. So we say that the limit of fx as x approaches c of this function does not exist. Okay, so I hope you understand my explanation about the mathematical definition of limit, which consists of epsilon and delta. Thank you.